Hi everyone, so this is just going to be a quick video explaining some of the core concepts of Tut6. This is all sort of summarized in Prof. Bester's guide, so this is just going to give some examples and some more ideas about the Tut. So I've broken it down into 4 steps. First we're splitting the IEEE float, then we've got to prepare it for the algorithm, which is the algorithm given on page 4. Then we execute it and obviously send back the answer. So first I wanted to talk about the stack here, so because this is where I was getting a lot of my bugs, and it's mostly about the offsetting. So this is nothing new. We've got the EVP return address above it, then we've got the variables pushed onto the stack. This top half, this is all old news, and this is all out of our control. You know, this is all given sort of by the function prototype. It's the bottom half that's sort of new for Tut 5 and 6. So this is where we percent define our own variables. So this -1 here is basically saying that S1 is 1 byte big. This difference between -2 and -6, that's 4. So that implies that F1 is 4 bytes big. Just remember afterwards, after you've percent defined all your variables, to subtract the right amount from your stack pointer. And that's always the maximum that you subtract, so it's going to be 6 in this case. Okay, the next bit of theory here is splitting via shifts. If you look at Prof. Bester's guide, he actually talks about the shift functions in there as well. So this is just an example explaining sort of the assembly semantics. If we've got a var1 and we shift left the var1 by 4, we're going to arrive at this result. So what we're basically doing in this example is we're trying to isolate these 4 green bits. So you'll notice that there's some new zeros there where we've shifted. Shift left always has new zeros. Shift right, we're going to shift right by 11 and isolate it to these bottom 4 now. And these are all the new zeros that have come from this right shift. That's because this has been a logic shift. You do get an arithmetic shift right, so that's SAR, I believe. So this is just an example of how we could possibly isolate these 4 bits if we wanted to. Okay, the next part is just an example using the registers. So I got this picture from a textbook. I found it pretty useful. So let's say I've got our EAX register. It's a 32-bit register, and we just want to isolate the bottom 8 bits. So let's say, for example, maybe I've got an 8-bit exponent that I want to move into. I could say move AL E1. So that's basically isolating the bottom 8 bits and moving E1 into the bottom 8 bits. Just a note that I've added here is clear EAX before you do this, because the top 24 bits, for example, will be left unchanged. And that might give you errors on your calculations further down the line. So XOR EAX is just the sort of fastest way to clear out your register. We've seen that in the earlier Tuts as well. This is just on preparing the float for the algorithm. So we can see this is the IEEE standard, and this is not the IEEE standard. This is actually 33 bits because it's been expanded. So what we've done is we've taken the bias away from the exponent by adding 127. So this is 134, I believe, and this is 7. So this is how we prepare the exponent, and how we prepare the fraction is we put a 1 in front of it. Just a bit of note here that I've added is you don't put a 1 in front if the fraction is all zeros, i.e. if it's a 0 float. Sorry, that's sort of cut off there. Yeah. Don't put JBit as 1 in front of in front if the float is 0. This bottom figure, that's taken care of by the algorithm. This is going to be executed by while loops and all of that. You can look at page 4 for context. So this is basically just explaining the thinking behind the algorithm. These and the further steps. These are a couple notes about the actual prototype that Prof. Bester gave us. If I can scroll down here a bit. Jeez. Okay. So this assumes the float has already been prepared. So it's not going to be IEEE standard. So the exponent is no longer biased, and we've put that j bit in front of the f. So that's an important assumption about this whole prototype. Division, obviously I've added a note to use shifting rather than the IDiv. The 2's complement negation, that's also given by Prof Best and the spec. We can just use this command neg eax. Sorry, fighting with my software here. Important note here is not to try and normalize a fraction that's 0, because you're going to be stuck in infinite while loops. So if you do have infinite while loops, this is probably one of the first places to look if you've got the normalization going. This confused me for a little while as well. This bit 31 to 24, this is really the left chunk, because we're counting from right to left in this case. So this is bits here, 31 to 24, that we're checking. While bit 23 is not equal to 1, a way we've done this in the past, if you look at our ample as well, is we can test individual bits. So if we test, for example, I've got something like var1, sorry, that's a bit of a squiggle there. If we test var1 with 8, we're basically testing if the 4th bit is switched on, and then jnz is jump if it's not 0. So that's a sort of a sneaky way to test individual bits, and it comes in very useful. Obviously, you don't need to specify this in decimal. You can use something like hex or binary, whatever you prefer. Okay, just a further note here is on combining and copying. So this is once we've isolated things and we're ready to put the data together. We've already performed all the functions. So let's say I've got a var1 with some data at the bottom, a var2 with some data at the top, and I want to combine it. So if you look at our ample bit masking, it explains it quite well. So what we can do is we can just use the OR operation, and that combines all the data quite nicely with the top and the bottom, and stores the result in the first operand. So it'll store it in var1. var2 is unchanged still. This is just the last bit of info on pointers. So for example, let's say we've got some data in eax, and we've got a %defined variable, pointer here, and we want to move data from eax into the pointer. One way to do this is to move the pointer into a register. Then we move brackets around the register, ebx eax. So what this is doing, it's almost like in C when we put the star in front to dereference. I know that's technically not correct, but that's sort of the way I think about it in this specific case. This is just a reasonable way to do it. And then all the data is going to be moved from eax into the address where our pointer is pointing to. Okay, I hope that explained some of the core ideas. There are some more technical things, like I think when you've got variables with, or you've got values with equal magnitude and opposite sign, but that's explained really well by Justin in the group chat. I think it was on Thursday. There was a bit of discussion about that, and basically if you sort of follow Justin's advice, you'll be pretty sorted for that area. But this should get you passing most of the test cases, and then you can kind of go from there. So I hope this has been useful, and yeah, good luck for the TUT and for obviously the next TUTs.